So this is question number 1 on your 2013 midterm. And in question number 1, the parameter of interest is monthly revenue at this engineering company. Okay, so let mu stand for monthly revenue. And our population of interest is all months that the engineering company has been in business for. And to infer or get a better idea about this mu, what you have done is you have sampled 6 months and you have measured the revenue for each of those months that you've sampled. So for example, the first month that you've sampled is January 2002, and that was $83,000 in revenue, $105,000 in revenue for December 1995, and so on and so forth. So based on these 6 observations that we've made, we want to generate, the question asks, a 75% lower bound for the average income or revenue in a month. Okay. So here, guys, because it's a lower bound, it's no longer a two-tailed confidence interval. So the lower bound of for mu is given by x bar minus z alpha times sigma over root n. Notice that I don't divide alpha by 2 as I had done when I was computing a confidence interval, okay, where I was computing both a lower bound and an upper bound. Okay. We are told in the question to assume that the standard deviation of the monthly revenue is 45,000. Okay. So that takes care of sigma. We know what n is. N is equal to 6. X bar, I forgot to put the x bar there, has to be estimated from our 6 data points. Okay. So we all know how to calculate x bar. Okay. Add up or take the sum of all the x's divided by n. And I've done that calculation for you. And where's my x bar? My x bar here is $121,833.33. Okay. So the last thing remaining is to find the Z alpha. Okay. Remember, alpha is always equal to 1 minus the confidence level. Our confidence level that we seek is 75%. So alpha is 25. And Z alpha is basically the value on the standard normal table such that that area is equal to 25%. So we're looking for Z sub 0.05. And that's going to make up our alpha. So how do we find this? We have to go consult the standard normal table. Okay, well, that is the same thing as finding the value of Z such that the area on this side, on the left of this particular Z value, is equal to 75%. Okay. So I have a snapshot of my standard normal table here. Okay, so as you can see, when Z is equal to, let me change color here to see it better. When Z is equal to, let's see, 0.67, the area to the left of 0.67 is 74.86. So what that means is if Z were to be equal to 0.67, then this shaded region will be equal to 0.7486 as such. If it were to be equal to 0.68, okay, then the area to the left of Z will be equal to 0.7517 here. Okay, so obviously the Z-score that we're looking for has to be some value in between those two. Okay, so to find that value, we need to linearly interpolate. Okay, so the interpolation, since we didn't do this during the session, okay, let me fully demonstrate a perfect working example of linear interpolation here. Okay, so let's see. So let me write this down. Okay, when Z is equal to 0.67, okay, the probability to the left of 0.67, which is usually denoted by phi of 0.67, is equal to 0.7486 as per the table here. When z is equal to 0.68, phi of 0.68, or the area to the left of 0.68 underneath the standard normal curve, was or is equal to 0.7517. Okay. So the guy that we are after is the z 0.025, such that phi of that number, z of 0.025. Oh guys, I made a mistake. This should have been 0.25 all along. Okay. So let me just erase that. How do I make this eraser smaller? There it is. Okay. So that should have been 0.25, not 0.025. Okay. So let me just make that correction there. Okay. So phi of z 0.25 has to be equal to 0.75. And the guy that we are after is this guy here. Okay. So the interpolation means that if I were to take the difference, the slope using this and this, I get 0.67 minus 0.68 over, that didn't work out too well, over 0.7486 minus 0.7517 has to equal to the slope of this. Let me label that as x and x. Okay, so z sub 0.25 minus 0.68 divided by 0.75 minus 0.7517. Okay. And I trust that we can all do this algebra to solve for the unknown value of z sub 0.25. And you will find that that is equal to 0.6745. Okay. So now that we have the z value, okay, we have every ingredient that is needed to compute the 75% lower bound. So the 75% lower bound is equal to x bar, which is 121,833.33 minus 0.6745 times sigma over root n. And sigma was equal to what? Sigma was 45,000 and n was equal to 6. So take the square root of that. So multiply that together. Okay. If you compute this, let's see, where is my answer? If you compute this, you will get a lower bound of 109,524.64. Okay. We therefore say we are 75% confident that the true average monthly revenue is greater than $109,524.64 as such. Okay, so part B. So to answer part B, what we need is we need to get a feel for what a 90% lower bound for mu would be compared to 109,524.64. Okay. So if we were to compute this, you'll notice that in the equation of the lower bound, okay, nothing will change except the z alpha, okay, where alpha is going to be 10%. So if we were to compute a 90% lower bound, alpha will be 1 minus 90% or 10%. And that z sub 0.10, is it going to be bigger or smaller than z sub 0.25? And graphically, you could probably already see that z sub 0.10 will be somewhere over here. Okay, that will be my z sub 0.10, which implies that the value of z is bigger than the value of z sub 0.25. If z is bigger than 0.6745, what's going to happen is our confidence level is going to be smaller than 109,524. Okay. So in the question, in part B, it says that, what does it say? It says that the 90% confidence level is at least $90,000. Okay. We had just reasoned that the 90% confidence bound, or the lower bound, should be smaller than 109,000. Okay, and this lower bound that the manager or the director has computed is consistent with the one that we've computed in part A. Okay. So therefore, the answer, okay, if I could formalize it, looks like this. So yes, the answer is yes, it is consistent, since $90,000 is less than 75% lower bound that we had computed to be $109,500. It would be inconsistent if he had computed a 90% lower bound that is something greater than $109,524.64. That's not the case here. Therefore, the 90% lower bound that the director has computed is consistent with the answer that we found in part A.